This lesson is about why polyolefin fibers. Recent trends for fiber-reinforced concrete are in the context of high-performance concrete, taking advantage of the combination with other concrete technologies, such as self-compacting concrete or high-strength concrete. The advantages and synergies of these combinations will be studied in more detail in the last session of this course. For example, research has shown with steel fibers that the flux of self-compacting concrete tends to improve the residual strength of fiber-reinforced concrete due to the better orientation of the fibers, which is decisive in the fracture results. In addition, the use of new advanced materials has enabled the production of polyolefin fibers with improved properties and able to provide the concrete with structural capacities. In recent years, the efforts of plastic industry have allowed the production of a new generation of polyolefin fibers based in synthetic microfibers that are inert in an alkaline environment and provide concrete with structural capacities to substitute traditional concrete steel reinforcement. The shapes and surface properties of this type of fibers can vary and is still a matter of research. At the time of producing this course, the best results have been obtained with fibers with the aspect and overall properties in these images. Regarding their geometry, manufacturers produce commonly fibers 48 and 60 mm long with an equivalent diameter usually of 0.92 mm, and note the embossed surface with the aim of improving the interface between the fiber and the matrix and the good mechanical properties. Concerning physical properties, their density is 0.91 grams centimeter cube, reaching an ultimate tensile strength of 500 megapascals. Elasticity modulus typically ranges from 9 to 20 gigapascals depending on the manufacturer. It is worth to highlight that the values of elasticity modulus are becoming closer and closer to that of concrete. It is unavoidable to compare their properties with those of steel fibers. Note that these two types of fibers, steel and polyolefin ones, are those considered in the standards as structural fibers as we are studying in this course. If we see the wide range of fibers, these two are produced with the aim of total or partial substitutions to traditional steel rebars. As previously explained, the last generation of polyolefin fibers have reached values of modulus of elasticity close to those of concrete, therefore enhancing their effectivity and the effectivity of the system matrix fiber. Geometries of the structural fibers are in the same order of magnitude, being the same is noticeably different. While the steel fibers are commonly improved by mechanical anchorages such as hooked end or crimped fibers, the polyolefin ones are improved by rust surfaces. Also note that the microsynthetic fibers, commonly named polypropylene fibers, are not structural. Not only their mechanical properties are lower, but also their size are remarkably smaller. In addition to cost reduction of the material, the outstanding advantages rely on their chemical stability, improving durability of the concrete. The production is also cleaner than that of steel. Not only the lower weights, but also the ease to handle, lighter and safe to reduce pan wear, etc. In addition to their low density, polyolefin fibers have good tensile properties, abrasion resistance, and excellent endurance in chemical aggressive environments, which, added to low cost, place them as an alternative to steel solutions when meshes or fibers are used. Nowadays, polyolefin fiber reinforced concrete has considerable residual tensile strengths and lower weights in comparison with steel fibers. Both researchers and the construction industry have made significant advances in the application of plastic fibers to reinforce concrete. Additionally, polyolefin fiber reinforced concrete has multiple sustainable benefits that have justified new research, given that in both use and end-of-life cycles of the material has limited impact compared with the common practice of using steel reinforcement. The lower dosages in terms of the weight needed to reach similar strengths reduce the costs of transport and thus the carbon footprint of the life cycle of the material. Derived from the production method, significant decreases of carbon emissions compared with the production of steel can also be found in literature. Plastic fibers can be directly mixed with concrete without clustering problems and with a reduced impact on workability. Also, by using ready-mix tracks, published research has shown that the loss of fibers is somewhat limited in comparison with the steel fiber. Let's summarize. A new generation of plastic fibers with improved mechanical properties and surface treatments can meet the requirements of the standards to be considered as structural fibers. Therefore, their contributions allow reduction of substitution of the steel reinforcement. The handling of this type of fibers is safer and lighter and saves time in operations, such as preparation and placing of the wire mesh. These aspects permit continuous production of a concrete setting with a consequent reduction of labor costs to have about half of those in the case of using steel. In conclusion, mainly due to the lower cost of the material for certain elements and the lack of corrosion when subjected to hazardous environments, the use of this type of fibers has become attractive. The previous statements are based on this bibliography in case you have access to it. Otherwise, the supplied bibliography can be read for a deeper comprehension of this lesson.